Hello friends, we will now see one university question on displacement method, matrix displacement method. This is the university question for Annamalai University in the year May 2015. It is a two-span continuous beam. You can see the spans AB, BC, and A is simply supported, B is simply supported, and C is fixed. And one span is loaded with point load, another span with uniformly distributed load. We have to analyze this continuous beam by matrix displacement method. First, we have to calculate the two displacements. How many displacements are there in this structure? There are two displacements. One displacement is at A in the form of rotation, that is theta A. Another displacement is at B, again in the form of rotation, that is theta B. These are the two displacements. There is no rotation at C because it is fixed. Here the rotation is 0. There are two displacements, theta A and theta B. So the degree of freedom is 2. That is, the kinematic redundancy is 2. Kinematic redundancy, degree of freedom, both are same. We have to calculate these two displacements. The procedure involves assuming the structure as a fixed beam and calculation of the fixed end moments first. So if you assume AB and BC as fixed supports, then these are the fixed end moments. M of AB is minus WL by 8 because it is in the anti-clockwise direction. M of BA is again WL by 8. It is positive in the clockwise direction. M of BC is minus WL square by 12, anti-clockwise movement with my negative sign. M of CB, WL square by 12, clockwise movement, hence with positive movement. Now we have to calculate the unbalanced moments at B and also at A. These are the 2 points where the displacements are there, theta A and theta B. At theta A, the unbalanced moment is minus 1.875 kilonewton meter. It is nothing but this moment. Similarly, F2, that is F2 means displacement number 2. F2 is displacement number 2. That is theta B. There are two moments. One moment is 1.875 and another moment is minus 6.767. So it is minus 4.795. These are the two unbalanced moments introduced because of the assumption made as if the beam is a fixed beam. Now we will calculate, we will apply unit rotation at displacement number 1 and calculate the moments induced at 1 and 2. Similarly, we will apply unit rotation at B and calculate the moment induced at B and A. Here this is displacement number 1 and B is displacement number 2. At A you apply unit rotation and find out the moment at 1 and 2. So that is what is written as stiffness coefficient K11. The second subscript 1 denotes the point of application of rotation. The first subscript denotes the moment induced at the respective point. So K11 means the moment induced at 1 due to rotation applied 1. That is equal to 4EI by 3. The formula is 4EI by L at the near side moment. You are applying the rotation at 1. You are calculating the moment at 1. So this is the near side moment, means 4EI by L. So this is the value. Now what about similarly for this unit rotation applied at A, what is the rotation? What is the moment induced at B? We have applied unit rotation at A and we have calculated the moment at A. Now, for the same unit rotation applied at A, what is the moment induced at B? That is what is represented as the stiffness coefficient K21. 1 is the point where the rotation is applied. 2 is the point where the moment is induced. So that is equal to 2EI by L, because this is the point where the rotation is applied and this is the point where the moment is induced. It is farther side. Farther side means the formula is 2EI by L. So this is the value. Similarly, K12 we will calculate. Here the rotation is applied at B and moment induced at 1 is calculated. The second substitute is 2. Rotation is applied at B and moment induced at 1 is calculated, which is farther end. So 2EA by L, and this is the value K12. Now next is K22. So the second substitute is 2. That is the rotation is applied at 2 and moment is induced at 2. Here at point 2 refers to the displacement theta B. On either side you have one span. BA is one span, BC is one span. Now you are applying rotation at 2 and calculating the moment induced at 2. That means near side moment. Near side moment means 4EI by L. So for the span AB, you have 4EI by L, that is 4EI by 3. And for the other span, you have 4EI by L, that is 4EI by 4. Both the moments you have to add, and this is the value. And these are the unbalanced moments, which is the sum of the fixed moments. This is the sum of the fixed moment at point 1. And this is the sum of the fixed moment at point 2. Now, what is the principle? The given structure is converted into a fixed beam. From the fixed beam, we have to deduce the given structure. What are the difference between the given structure and the assumed structure? In the given structure, there are two rotations, theta A and theta B, which is not there in the assumed fixed beam. And there is no unbalanced moment at A and B in the given beam, but there is an unbalanced moment in the fixed beam at A and B, that is F1 and F2. Now we have applied that theta A and theta B are the actual rotations. So if we apply the rotations theta A and theta B, the moments induced at A and B should be such that they are equal and opposite to the unbalanced moment. That is the basic equilibrium equation. So this is K stiffness coefficient into the delta. Delta is the displacement. Here the displacement is theta A and theta B. K is the stiffness coefficient, that is the four values K11, K12, K21, K22, they are calculated. This is the stiffness and this is theta A and theta B. So this is the total moment induced due to rotations theta A and theta B, because the stiffness coefficient refers to the moment caused by unit rotation. The actual rotation is theta A and theta B. So if the moments are multiplied by theta A and theta B, this gives the total moment caused by the rotations, and that should be equal and opposite to the unbalanced moment. So that is minus sign, because equal and opposite, and the fixed moments, the unbalanced moments that is F1 and F2, and they are written here. So this is the basic equilibrium equation used for solving the two unknowns theta A and theta B. The rest is matrix algebra. You can see in this equation. This equation, the only unknowns are theta A and theta B. All other things are known. So in terms of EI, you can calculate the value of theta A and theta B, and they are calculated. EI into theta A is equal to this much. EI into theta B is equal to this much. You can see this. Now we have calculated theta A and theta B. The rotations are known. Now we have to calculate the member end moments. We have the relationship for the member end moments. Here the moment MAB is equal to 0 because A is simply supported. Therefore, the end moment MAB is equal to 0. There cannot be any other moment. Then only the sigma A M is equal to 0 will be satisfied here. MAB is equal to 0. Now, what about MBC and MBA? MBC is equal to M of BC, that is minus 6.67 plus 2EA by L into 2 theta B. This is the rotation at the near end. Therefore, 2EA by L into 2 times theta B. This is fixed end moment. So MBC is equal to the fixed end moment plus 2EA by L. Theta B has been already calculated. You can substitute the value of EA into theta B here. Then you will get this moment. This is the Hagen moment. MBC is equal to this much. MBA should also be equal and opposite. Therefore, it is also Hagen moment. It is 4.74. And MCB is M of CB, that is the fixed moment, plus 2EA by L into theta B. Theta B is the farther side rotation. Therefore, theta B is there. If it is near side, it should be double. So M of AB plus 2EA by L into the farther side, M of B plus this much, 2EA by L into theta B. So this is the moment here. And this again is Hagen moment because positive side. Now M of CB is positive. Positive means anti-clockwise. M of CB. This is clockwise. Clockwise means positive. And this clockwise will cause tension at top. Therefore, it is Hagen moment. Positive means clockwise. At C, clockwise means tension at top. Therefore, it is Hagen. Now we have listed these moment values here. Now we have to plot the bending moment diagram. For the span AB, you have to calculate the effect of simple bending moment diagram and the fixed bending moment diagram. And you have to calculate the net ordinate. Now at D, the simply supported bending moment is WL by 4, 5 into 3 by 4, WL by 4, minus the effect of the Hagen moment. At A, it is 0, at B, it is 4.74. Therefore, at D, it will be half of 4.74. So it is this much. This is the sagging bending moment and this is the Hagen bending moment. So the net effect is 1.38 kilonewton meter, and that has been written here. At A, the moment is 0 and here it is 1.38. At B, it is 4.74 ton-meter Hagen bending moment. Between A and D, there is no load. So the relationship for bending moment diagram is linear. Between D and B, there is no load. Relationship for bending moment is linear. Now, what about bending moment at E? One is the simply supported bending moment. BC is subjected to uniformly distributed load, 4 kN/meter. Therefore, it is WL square by 8. This is simply supported bending moment minus the effect of the fixed moment. Here you have two fixed moment at B and C. They are 4.74 and 7.63. E is the middle of the beam BC. Here the fixed moment value will be average of these two. 4.64 plus 7.63 by 2. 4.674, 7.63 by 2. This is the sagging bending moment. This is the hogging bending moment. And this is greater. Sagging moment is greater. Hogging moment is smaller. And it is equal to plus 3.82 kN/meter. Please note, it is an error. It is not minus 3.82. It is plus 3.82. Sagging moment is greater. It is 10 plus something, this first term, and minus this second term. It comes to plus 3.82. This minus sign is error. 3.82 kN/meter sagging moment. So that is been plotted here. Between B and E, there is one uniformly distributed load. So the bending moment relationship is curvilinear. It is second order. Between E and C, there is one uniformly distributed load. Therefore, the bending moment relationship is curvilinear. It is plotted like a curve. This is the bending moment diagram. The purpose of plotting the bending moment diagram on tension side has some merit, because in the case of RCC beam, generally the reinforcement is provided on tension side generally, but compression side also provided reinforcement as an additional requirement. That is different. It is very important to know the tension side. So by seeing this bending moment diagram, people can visualize, yes, at D, the tension is at bottom. At B, the middle support, the tension is at top. At E, again, the midspan of BC, the tension is at bottom. We are able to visualize whether the tension is at bottom or top. And that is the reason for plotting the bending moment diagram on tension side. Now, this is the worked example of one university questions. Now, if you visit this website, https://rgnsite.wordpress.com. In brief, it is rgnsite.wordpress.com. Repeat, rgnsite.wordpress.com. If you visit, you will find hundreds of university questions and answers on various topics: RCC design, steel design, strength of materials, structural analysis, matrix methods, force method, displacement method. Not only the solved examples of university questions on these topics, but also the explanations. For example, how the relationship is derived between the fixed end moment and the member end moment. What is the relationship for the moment induced due to the rotation applied? All these explanations are given in this website. How the given structure is assumed and idealized as a fixed beam, and how we are deducing from the assumed fixed beam to the actual beam by applying rotations. All these explanations are given in that website. The equilibrium equations also have been explained, both for force method and displacement method. Somewhere around 25 university questions had been solved only on matrix methods. In this website, you can find a lot of university questions and answers on deflection of beams, strain energy method, slope reflection method, moment distribution method, RCC design, and steel design. So please visit this site, rgnsite.wordpress.com. Also pass it on to other engineers and students. Thank you.